given U, which goes from omega in Rn into Rn, where n is bigger than or equal to 3, that satisfies this differential inclusion. And recall, this is just a set of lambda times rotations, where lambda is positive. Then, for some A and B belonging to Rn, and some, I think we called it C, or let's say C, such that C is an affine mapping, such that this is just some affine, or you can take its linear. Oops. We have that U, let's write U of x instead. U of x is the inversion mapping around the sphere centered on A, composed with a reflection, Q, composed with this linear mapping plus some constant B. So where I of x is just this thing, x over mod x squared, and Q is just a linear mapping whose matrix looks like this. It's just reflecting through the first coordinate. Like this. It's the diagonal matrix whose only entry which is not equal to 1 is -1 at the top here. So it's just reflecting through the first coordinate. Yeah? And the point was that the real action of this is this guy, which reflects through the surface of the sphere. Yeah? Q reflects back so that we get something which is orientating, preserving. C, we can obviously multiply by any linear mapping which has got gradient inside this and still have a differential inclusion into this space. A is arbitrary, we can reflect through any sphere, and we can add any constant and not change the properties of the differential inclusion, right? So it's an extremely prescriptive set of mappings. I mean, it's defined by these finite number of parameters. So this is a very, very restrictive class of mappings that satisfy this, and therefore there's no interesting theory, right? So no higher dimensional complex analysis. Okay, so this is something you're going to learn later, that there's a natural generalization to spaces like C1, C2, C3, which is actually for purposes of analysis, a more meaningful version of that, where instead of insisting having pointwise derivatives, we have weak derivatives, and we can actually have things that form Banach spaces and therefore take limits and stay within inside these spaces. And it's an open research question as to what is the minimum regularity for the mappings U, such that this actually still holds true. For even dimension, it's known, and the regularity is, well, it's no point in me saying because I haven't explained Sobolev spaces yet. But there's a neat answer and a neat conjecture, which is known for even n, but it's open for odd n. So this has been an open question for a long time. What is the optimal regularity for which this actually holds true? I said C3 because I think that's the original regularity of Liouville, but it's not particularly hard to replace this by C1. But the actual proof of this is quite hard. It's quite a technical, difficult computation. So we're not going to prove this. We're going to prove a special case. So, special case. Suppose we have so the same hypothesis U from omega contained within Rn into Rn. Let's just take U to be C1. And du belongs to the space of rotations everywhere. Then what would you conclude about the mapping U based on what I've told you about Liouville's theorem? Obviously, this is a stronger hypothesis. The rotations are contained within the conformal matrices. So, okay, well, that's actually true. That's actually the right guess. So then we actually have that U is affine, and du is just a fixed rotation. Right, the u of, just to emphasize this, the u of x is just a fixed rotation for every single x. Okay, and you can kind of guess this because of the following. So we can guess. Let me just underline the statement. Because if we have, let's just take omega to be convex, just for simplicity, and take points A, B belonging to omega, then, by the fundamental theorem of calculus, then u of A minus u of B is the absolute value, integrating from A to B, of the u of x acting on this vector B minus A over B minus A like this. And I write dH1 because it's the one-dimensional measure on this thing, but you can understand this as just the ordinary one-dimensional line integral, and I'll write down what I mean in a second. Okay, so we have this guy here is a rotation, right? This guy is the thing of unit length. Yeah? So if we put the absolute value signs inside, we have that we're just integrating over this thing, something which has got length 1, right? Because if you take a vector of length 1 and you rotate it, it's still a vector of length 1. h1 of x, and therefore that's less than b minus a. Yeah? So in particular, this thing is what we call a one Lipschitz mapping. Right? Have you guys heard of this concept of a Lipschitz mapping? All right, good. So let's look at this. So what did we do here? We are just applying the fundamental theorem of calculus. So maybe here I put a little box what I mean by this. So you've learned about doing one-dimensional line integrals. So given a path or a curve, in complex analysis we call this a curve. Gamma, or actually let's call it C. That gamma from A to B be the parameterization into C, and then we write this. So this is what I'm going to mean by a one-dimensional integral. I'm going to write dh1 and then maybe dx like this. I'm going to be integral from A to B, f of gamma of s, absolute value s prime, like this, ds. Just the ordinary one-dimensional integral across a curve. Yeah? When you learn more measure theory, you will learn that there's actually a natural measure we can put on any one-dimensional object called Hausdorff measure, and therefore we denote it by h1. Okay? So I'm going to write h1 because in the future that's what you're going to see, and we don't need to do this. This thing only works when we have a nice thing that we can parameterize, but we can do this for any nice one-dimensional object. So I'd rather, write it in the more general form. But for those of you who haven't seen this yet, everything I'm doing here is smooth. Everything I'll do, every line integral I'll do will always be smooth, so you can always understand it in this form. And of course, these things agree when we have a smooth curve. Cool. All right, so we're using the fundamental theorem of calculus, right? This is just the fundamental theorem of calculus. Yeah, this is just the fundamental theorem of calculus. So if you're uncomfortable with this, just think about how we are applying it to every single coordinate of u, like this, which gives out a vector, which we integrate, and that gives us the difference between these two guys. So if you feel rusty about multivariable calculus, look carefully at this step, check it out. You will see that this is something you believe, okay? And talk with me in office hour if you still feel not so clear about it, okay? So we do this, and then the u is a rotation. This is a 1 vector, So when we put the absolute values, signs in sign, then this thing has got length 1, So we're just integrating something of length 1 over the curve a to b. Therefore, it's just the length a to b. All right, people, how do you feel? Does this make sense? Cool. So this is what is called one Lipschitz. So we say an arbitrary mapping, say G, is Lipschitz, or you can even say what Lipschitz is, say M Lipschitz. I think that's not how you spell it. Okay. I'm going to write just M lip. If and only if we have that g of x minus g of y is less than m of x minus y, like this, okay? So this is a very strong control on how much g oscillates. And that's what we have for this. We have that this mapping is a 1 Lipschitz mapping. Cool. All right, I'm going to erase the board. This thing should be a hint to you why the inversion mapping can't be part of U under this hypothesis. I want you guys to think about that while I erase the board and tell me why so. Okay, suggestions. Why did this little calculation imply to us that there's no inversion in the decomposition of a mapping which has got a gradient directly into rotations? If we have that the ball of radius 1 intersect A, intersect omega is not equal to the empty set, where A is the mapping, A is the point around which we center the inversion mapping, then what do we have? So we have omega. This, for example, could be our guy here, our inversion, and then we can take 2 points in here, x and y, and then when we act on them with the inversion, they'll be mapped along this ray to 2 points which are further out. And that is not what we'd expect for a 1 Lipschitz mapping. And maybe that could be compensated for by the other parts of the decomposition, but it starts to give us some hint that this kind of behavior is not what we expect when we have something which is 1 Lipschitz. If the guy actually didn't intersect omega, then we wouldn't have this phenomena, but we would have the phenomena for the inverse if some kind of inverse existed. Okay? So it's not a completely trivial thing, but it is giving us something of a suggestion. Okay. Then I of x minus a is not 1 Lipschitz on omega. Okay. So that's certainly not a proof, but let us try and we're going to prove it we're going to sketch an elementary proof, and then we're going to do a more modern, sophisticated proof, which will give us an indication of how a much stronger result can be proved. So, elementary proof, or maybe it's a sketch of an elementary proof, because I'm going to use things inside this that I'm not going to prove. So, sketch of proof And we're going to do this just in 2 dimensions in R2. And we're going to make the assumption that U is actually globally invertible for invertible U. Okay, so how would we do this? Well, we've already learned that it is 1 Lipschitz, right? So we know that U of A minus U of B is less than or equal to A minus B for any A comma B inside omega. Again, we're going to assume omega is convex. So then the line segment connecting A to B is still inside omega. Yeah. Then let's draw a picture. So we have, this is omega. We have, let's make it bigger. We have A to B. It is being mapped to something, okay, like this. Actually, let's make them not bigger, but smaller. A and B somewhat in the interior like this. These are mapped to these points, U of A, U of B, right here, okay? And for example, let's give them names. Let's call that alpha, and let's call that beta, okay? Now we're going to assume that we are sufficiently inside the interior of omega that when we connect the line segment that joins U of A and U to B, then it still stays inside the image. This is an assumption. This is not trivial. We have to have some arguments for why this is true, but let's assume. So, assume that the line segment U of A, U of B is contained within the image like this. Okay. Then, what would we like to do? Well, the natural thing is to use invertibility, right? And to go back like this with the inverse. And what is cool about this idea is that we know about the gradient of the inverse, right? So we know that the u to the minus 1, let's not use x, let's use zeta. What is it? It is du of u to the minus 1 of zeta to the minus 1. Again, this is from multivariable calculus, right? We know about the inverse of a gradient. Yeah? But if we look at this guy is inside the space of rotations, and we're taking the inverse of a rotation, right? Which is also a rotation. Yeah? So then this thing also belongs to the space of rotations. Yeah? So if we integrate between alpha and beta with the inverse mapping, okay, then this thing, let's put it over here, this thing is u to the minus 1 of beta minus u to the minus 1 of alpha. Again, fundamental theorem of calculus. Let's put the absolute value signs around it, and absolute value signs around this. Okay, and then exactly, and also I stated this wrong. This acting on the vector beta minus alpha over beta minus alpha, absolute value. Theta like this. Okay. We put the absolute value signs inside again. This thing is a rotation. This is a unit vector, so then this is less than the length alpha minus beta. But again, alpha is u of A. So this is u of A minus u of B. Okay. And what we know from this thing, alpha again is u of A, so u to the minus 1 of alpha is just A, u to the minus 1 of beta is just B, right? So then this gives us that A minus B is less than or equal to u of A minus u of B, right? The opposite inequality to what we have there. So we have that u of a minus u of b is equal to a minus b. And this, as you can imagine, is something pretty strong, right? This is something pretty strong. So let's look at this thing here, the line segment A to B. This gets mapped to something which connects u of a to u of b. Potentially it could be some wiggly line like this, yeah? But let's try and understand the length of this line, okay? So we also know just from calculus how to express length, right? So, or from multivariable calculus. But I'm going to write length as h1 of the image of the curve because, again, h1 is the natural way to measure one-dimensional objects. So I'm going to write this h1 of u of the line segment A to B. What I mean by this is just the one-dimensional length of this thing, and we learned how to do this in calculus, right? So given curve C, then the parameterization is given by gamma from A to B. Then we have that this thing, I should write this better. So given C as before, then the one-dimensional length, which I'm going to write like this, is, in terms of calculus, just like this. Right? This is what we remember from calculus. This is how we define the length of a one-dimensional curve. Right? It's independent of parameterization, and it's a well-defined thing. But again, you will later learn that we can just directly measure it even when there's no parameterization with a so-called Hausdorff measure. So that's what I'm writing h1, rather than just writing length in words. Is everybody with me here? Because you guys have different backgrounds at different stages. So some of you have seen this kind of stuff before. Some of you it's totally new. We have time. Just question me about anything which isn't clear. Are we all okay? Yeah? Give me a thumbs up if you're okay with this. Okay, super. So what is this? This thing is integral from over the line segment A to B of now I don't want to write the official expression. I just yeah, I do want to write this expression. So this thing is like this. It is the integral from A to B like this. It's the same expression as before, du of x of b minus a over b minus a like this. So previously I did this just to bound above, but now I'm saying that this is actually an equality like this. The h1 of x. Okay, so in particular, this gives that this is exactly equal to the length a minus b. Now let me, the parameterization gamma of t is equal to a plus t of b minus a over b minus a, like this. So this parameterizes our curve from 0 to 1, right? So if we use this formula above here, then this parameterizes our curve, A to B, but we want the parameterization of the image. So we're going to define gamma tilde of t to be u of a of t b minus a over b minus a absolute value like this, and then we are in good shape because gamma prime tilde of t is indeed equal to du of this thing, so I can write it directly as gamma of t like this, and then the derivative internally, which is b minus a over b B minus A. And then directly from this definition, H1 of U of AB is integral from 0 to 1 of 0 to 1. Right, if we differentiate this, right, so this is not from 0 to 1, this is from 0 to absolute value of AB, okay? For 0 less than t less than the absolute value of B minus A. So when we're at 0, we're at A, and when we're at absolute value of B minus A, we are at B. Yeah? Cool, so it's like this, and then just putting in this definition, we have it here, absolute value of du of gamma of t, B minus A. This, dt, and the way I've defined this thing, this is the same as this. So this is indeed the same because gamma is a parameterization of A to B. So anyway, so this is the same formula, A to B, like this. U of x, B minus A over B minus A. dH1 of x, okay? Or if you're uncomfortable with that, just take the absolute values right inside this thing. Either way, we get this. We get B. We get this is equal to or less than equal to. I think this thing is the absolute value of this, which is the absolute value of this, so it is equal to B minus A. Okay, so just put the absolute values inside here. We have it here. Yeah, this line is just to connect it to what we wrote before, because this thing is just a real valued function on the path AB. So if we stick in the parameterization gamma, then this is exactly like this. This is how I've defined H1 integral on a curve. In any case, just from here, we know that this thing has got unit vector times a rotation. So we just have one integrated between 0 and absolute value of B minus A, so it's actually equal to B minus A. Everybody happy here? Yeah. So on this picture, what does it mean for this curve here? What does it mean for this curve? It has to be a straight line, right? Because the length of this curve is exactly B minus A, and it connects points that are B minus A apart, right? Length B minus A apart. So we don't have that the image of this straight line is some wiggly curve connecting this. It has to be the straight line connecting this, yeah? In other words, we are mapping straight lines to straight lines into this situation. Yeah? Are you all with me here? Okay, cool. I'm going to erase the board. And as I do so, try and think how we can go from that to a proof of the full result. Well, let's take our region to be a nice thing like this. And let's take 3 points like this. A, B, and C, okay? And I'm going to connect them by line segments, right? And we're going to make this an equilateral triangle so that we have that A minus B equals A minus C equals B minus C equals some length we're going to call R. Yeah? And then let's map it with U. And we're going to assume that we're lucky and that the images of these line segments remain inside the image. Actually, now we don't have to assume that because we've already shown that they are line segments. So we definitely know that already. So we have the image of U of A, this is U of B, and this is U of C. Tell me about these guys, these 3 points here. What do we know about them? Jamie, I guess that's what you're about to say, right? Yeah, indeed they will do, because we know that u of a minus u of b is equal to a minus b and all the other guys as well, yeah? But we know something even stronger. Tell me about the image of the line segments that connect these guys. They're straight line segments, right? That's what we just showed, right? So this thing is a straight line segment which directly connects u of a to u of b, yeah? And this thing, the image of b to c, is this thing here, yeah? So if we take the actual image of this triangle, which is the union of these three line segments, it is exactly mapping onto another equilateral triangle, yeah? Yeah? Cool. So suppose we take some internal joining line between these 2 points here. Let's call this point x1 and this point x2. Yeah? Well, because we are just moving on a straight line as we go from A to B with the action of u, right? Then we're going to have u of x1 would have to be here, and u of x2 would have to be here, right? Because we're exactly moving along a straight line, yeah? Because, again, we've shown that the h1 measure of the line segment A to B is exactly a minus b, yeah? So that means as we move along here, then we are exactly moving along in just a linear fashion from u of a to u to b. Because if we did anything else, we would just not be able to reach it, right? We'd not be able to get to the other side. Yeah? Cool. So we do indeed have that these guys are mapped to the equivalent place on the equilateral triangle here. And if we consider the image connecting them by exactly the same argument, the image of the line segment has to be a line segment because length are preserved. Yeah? So we can fill out this equilateral triangle with line segments, and it's just connecting this way. Yeah? Yeah? So that all that's happening inside this triangle is that we are mapping whatever point we have here to the same equivalent point inside this triangle. Yeah? But what might be happening is the triangle is rotated, right? The size is the same. Yeah, the size is the same. Yeah, the side lengths are the same. The images of straight line segments are line segments. So we do indeed just have it mapped to this. So it'll be a rotation. It'll be a rotation times a reflection, potentially. Yeah? Because the reflection would also preserve all these lengths. Yeah? So that argument tells us that inside here, so this triangle is arbitrary. We can move the triangle around and actually put overlapping triangles which must behave the same way. So we actually have that du will belong to what we call orthogonal matrices. So I did this, I think, when this is a 2 by 2. So this is orthogonal matrices. You know? But we actually want rotations, and then there's another little argument that since the determinant of this thing is always positive, so since du belongs to rotations, okay. Let me say this in a better way. So what we have is that du is some fixed orthogonal matrix everywhere. But since we have that it belongs to rotations, it actually has to be a rotation. So du of x equals some, let's call it tilde, which is an orthogonal matrix. But just from this argument, but since du belongs to rotations everywhere, then the fixed matrix it has to be is one with determinant 1. It's a special orthogonal matrix. But then this thing actually belongs to S02, and therefore it's affine. Okay? So what have we shown? So if U is invertible, then du is just equal to R0 belonging to rotations. And there was a little bit of technicalities I was skipping over because we had to have some argument about why the image of the line segment is still inside the line segment enough so that when we connect it, we're still going to remain inside the line segment. But if we are deep enough inside here, then by some not too difficult arguments, we can show this, and then we can just expand outwards. So there is a way to actually do this, make this rigorous for invertible mappings. In fact, there's a way to do this for arbitrary mappings because arbitrary mappings are locally invertible. So we can actually push this forward and get a proof. But this is a kind of what we call an elementary proof in the sense we're not using much technology. We're working with our hands. It's maybe the most intuitive proof. It's the proof that most naturally makes sense to us, but there's a slicker, more modern way to prove it, and that's what we'll consider now. So, modern proof. Or at least we're going to start the modern proof. Okay, couple of key identities which are very useful. First identity. So let's define the cofactor matrix. So given A belonging to n times n, the cofactor matrix so let me define some notation. So I'm going to define B of ij equals the ijth entry of B. Okay, some notation of matrices. So the cofactor matrix is an n by n matrix, as you know, and it's given by this. It's given by -1, the ij, times I plus j, I guess. And then times the determinant of what I'm going to call A hat, ij, where A hat, ij, is this matrix in n-1 times n-1, which we get from deleting the ijth row and column. Okay, so first identity. We'll just do this in 2 by 2, but it's true in generality. So if we take a matrix, so if U belongs to omega, which is in R2, into R2, then its matrix is obviously a 2 by 2, right? So if we form the cofactor matrix, then I claim the divergence, and I'll explain what this means in a second in the context of a matrix. The divergence of the cofactor matrix, the U, is 0. So the divergence you're used to acting on vector fields. When we have divergence acting on a matrix, we mean divergence acting on each row, one row at a time, right? So I could, for example, write like this. So the divergence of the first row of this matrix is 0, and divergence of the second row is 0. Okay? This is a generally true fact for any differentiable function, and we're just going to see it in 2 by 2. So if we take the 2 by 2, and we take the cofactor of it, so cofactor of the 2 by 2, so first row. Okay, and the cofactor is equal to what? Then it is equal to u of 2 comma 2. So we take this guy, we delete everything else, we just have this thing, determinant of this thing, and then it's minus 1 to the 1 plus 1, so it's just this. Then we take this, we delete everything else, we're going to have minus u2 comma 1. Yeah? Then we take this guy, we delete this row and column, we're going to have minus 1, 2. And we take this guy, we delete this row, this column, we're going to have u1 comma 1. Yeah? So if we take the divergence of the cofactor of this thing, then it's divergence of the first row. So it's going to be u2 to 1, and then the second entry of this vector is this guy, so it's u2, 1, 2. Yeah? And let's do this guy right here. Then it's minus u1, 1, 2, and then u1, 2, 1. Right? So actually we need this to be C2 for this calculation. More generally we don't, but just for this special case. And then this is just 0, 0 in both of these entries. Yeah? Cool. All right, we're almost out of time, but let me just start to say why this is interesting for us. So if we take the rotation, so if we take A, which is a rotation matrix, then what we know that A transposed is its inverse. Yeah? That is what these guys do. I can explain this later if you want. So we have this. We also have the general formula for the invert. So, and in general, then for invertible matrix B, and what is the inverse? And b to the minus 1. It is the cofactor matrix of B transposed. That's called the adjunct matrix sometimes, over the determinant of B. Yeah? So if we have the U, which is inside the space of rotations, like this, yeah, then what do we know? We know that the U transpose is its inverse. Let's write point X. Okay. Which is equal to the cofactor matrix transposed. Over the determinant, but the determinant is just equal to 1. Yeah? Which means that the U of X actually is its own cofactor matrix. Yeah? And that is getting pretty exciting, because if we therefore, so I'm continuing down there, so if the U of X belongs to rotations everywhere, so this is true in generality. I've just done this proof for 2 by 2, but it's generally true. Then, by the above calculation, if we take the divergence of the gradient, which again means the divergence of each individual row one at a time, that's the same as the divergence of the cofactor, which is equal to 0. So if this is n by n, then this every single row is equal to 0. Yeah? Cool. But the divergence of a gradient is just the Laplacian. I know I'm overrunning. I promise this is the last thing I say. If we take the divergence of the gradient of any function, right, it's the divergence of f comma 1, f comma 2, f comma n, right? This is equal to f comma 1, 1 plus f comma 2, 2, f comma n, n, which is equal to Laplacian of f. Yeah? So this thing here says that every single coordinate of the function, of the vector valued function u, is harmonic. So if we write u of x has got coordinates u1 of x up to un of x, then from star we have that Laplacian of uk of x is equal to 0 on omega for k equals 1, 2, all the way up to n. Okay? So the differential inclusion into rotations implies already a very powerful thing. It's an incredibly special thing to satisfy the harmonic equation. We have many, many strong things following from that. And that's what we instantaneously get when we have a differential inclusion into the rotations. Okay? And that's going to be something we'll kind of, it'll be a kind of theme that we need to pay attention to, that differential inclusions into certain sets imply additional regularity because of the structure of the set. So we've already seen this in complex analysis, that the differential inclusion into two-dimensional rotations like this implied the Cauchy-Riemann equations, right? And the Cauchy-Riemann equations actually also implied that the coordinates uv of a holomorphic functions are harmonic. Here we have this in n dimensions, looks like a completely different direction, but it's also true. And this is one of the tools we're going to use to actually show the special case of Liouville theorems for rotations in the next class. Cool. All right. Sorry I overran. Thank you for your attention. I'll see you all on Wednesday. Have a great day, people.